Okay, good morning. Okay, today's class we will discuss the Carnot's heat engine, refrigerator, and heat pump. Almost everything, all three will have the same set of formulas. The formulas will be same as usual. So what we discussed for Carnot's heat engine, no, the same thing is applicable for refrigerator as well as heat pump. The end formulas are very important. So already you know the idea of efficiency, everything. Okay, let me start with Carnot seat engine first. Let me just move the pins. Okay, now we'll start like this. Carnot seat engine. So as we know, PV diagram. If you can go for the pressure, this is pressure. There's a volume. Okay, then now two isotherms. These are the isotherms. These are the adiabatic. So we'll take this as A, B, C, and D. Actually, it's a cyclic process only. The gas will start from A, it will undergo isotherms. So this is the AB, and AB is isothermal. Expansion. This is isothermal compression. Adiabatic expansion. Adiabatic compression. Okay, let's see that. And let the temperature here be T1. There's a, because isothermal expansion, T1. Again, isothermal compression, temperature at C equal to D equal to T2. Okay, let's take the 1 mole of gas. What will be that one? Okay, let's calculate the efficiency. What is AB? AB is isothermal expansion. Heat is absorbed or rejected. Heat will be absorbed. QAB, and here heat will be rejected. QCD. What will be the QBC and QDA? As in the adiabatic process, no heat exchange. Okay, we'll write that data. So QBC equal to QDA equal to 0. No heat exchange as their adiabatic process. So what's happening here? The adiabatic process, the two adiabatic curves will intersect isotherms curves that one. Let me show this. Yeah, it's okay. Look at now BC. These are the two isotherms are intersected by two adiabatic curves. Able to see this? So this is the two isothermal curves. They are intersected by adiabatic curves. The isothermal expansion occurs at temperature T1. The the isothermal compression takes place at temperature T2. And these are adiabatic process, no heat exchange. Okay, I want you to calculate the efficiency. Let's see that efficiency depends on what. Very important it is. Okay, try out now. Shall we go for area under PV diagram? What do you suggest? Shall we go for area under PV diagram? we can't calculate the area under the curve, no. So what is suggestible? Better let's go for heat exchange. That'll be much easier. Okay, try it. Already we have discussed, no. It'll be much easier for you to work out this one. Okay, calculate efficiency. I'm asking you calculate efficiency. Already we have discussed so many numerical. There's another numerical. Okay, first get me efficiency, then I'll come into the discussion. Anybody answer? Okay, I'll do one thing. I'll proceed. Q positive. What is Q positive? QAB is Q positive, no? It is absorbed. And QCD is what? Q negative. So what is in isothermal process? First we'll write it Q positive. Q positive is in fact QAB. N moles of gas. NR. T1 shall I write? Temperature of gas T1 log of VB by VA. What is Q negative? QCD equal to NR T2 log of VD by VC. Fine. So let's come for the efficiency. So what is the formula? Efficiency Q positive minus Q negative by Q positive. Now what is Q positive? QAB. So which is NR T1 log of VB by VA. Mod as usual. Let me consider NR T2 log of VD by VC. This will be NR T1 log of VB by VA. Agree this? Till here, I think no problem. Okay, now I have to proceed further. I want relationship between the volumes. I want to solve. NR will get eliminated. Okay, let's search for the relationship between the volumes. How the volumes of gas will be related. So let me take the adiabatic process into the picture. So how can we apply between B and C, adiabatic expansion, any formula for path BC? Yeah. TB BB gamma minus 1 equal to TC BC gamma minus 1. TB is what? T1. VB gamma minus 1. T2 VC gamma minus 1. So this I can rewrite it further. VB by, okay, this one, T1 by T2. Okay, this gamma minus 1, I'll send on to other side. T1 by T2, 1 by gamma minus 1 equal to VB by VC. Will I agree this? Similarly, we'll go for path DA. For the path DA, it will be T2, because temperature of gas at C and D will be same. I'm writing directly, or let me write it. TD Vd gamma minus 1, Ta, Va gamma minus 1. Td is what? T2. Vd gamma minus 1 is equal to T1 Va gamma minus 1. So T2 by T1, T1 by T2 is needed. No? Vd by Va gamma minus 1 equal to T1 by T2. Vc by Vb. Okay, no, yeah, I'll change it. Thank you. No, similarly, T1 by T2, this, let me, okay, try to see this. So shall we, this is the equation 1, 2, and 3. By taking help of for adiabatic process for the path dA, so we are writing this equation. So now, shall we equate 1 and 3? T1 by T2, 1 to the power of 1 by gamma minus 1 should be equal to, by equating 1 and 2. So what we can write from, sorry, 2 and 3. From 2 and 3, Vc by Vb is equal to Vd by Va. Let me replace Vb by Va. Or sorry, Vd by Vc I'll replace. Vd by Vc will be Va by Vb. Let me call this as equation 4. Very, very important. You have to remember, huh? This is very, very, very important. So shall we substitute equation 4 in 1, where all Vds is there, Va by Vb. So putting 4 in 1. Though, so therefore the efficiency will be n. Okay, this nr get cancelled. So therefore T1 log of Vb by Va, T2 log of Vd by Vc. So which is Va by Vb, all divided by log of T1 log of Vb by Va. As it is log, no, I can rewrite it. As it is in law, so sorry, as it is in mod, no, so we can write it as, okay, all of you, no problem. So log Vb by Va will get eliminated. So finally, what will end up? The efficiency, I'll just enter it as T1 minus T2 by T1. I think this is the first time we have come across equation of this kind. Will I agree, all of you? Because all the numericals were we used to substitute, we used to get some value. But here, so what happened? It is directly coming in terms of T1 and T2. So what they are T1 and T2? What they can be? The next question we have to ask it. So what are the temperature T1, T2? So T1, T2 are what, like the heat absorbed. Anybody wants to say anything about T1, T2? T1 is what? The temperature at which isothermal expansion occurs. What is the T2? The temperature at which isothermal compression is what takes place here. So then who will absorb this, the particular gas? So, okay, now here what happened? I'm going to design an heat engine. Okay, what all we discussed? I think this oh, already we have done so many problems. No, we have calculated efficiency of gas in one full cycle. The same method. This is what called as Carnot's heat engine. He has designed in such a way that he can control the efficiency. You look at all the previous problems. Do we have any control on efficiency? Anybody wants to like if you want to talk anything here, okay, you can really interact with the teacher now. Okay, previous all problems we have done. In all those problems, what was the issue? The efficiency was fixed. Am I right? All of you, can you recollect what all problems we have done? Am I right?
Yes, sir.
Hmm? So, say this is very important. If I just, I'll another 5 minutes, I'll end up this topic. In all the numericals, what all we discussed, the efficiency was a fixed value. We used to get say 20% or 5 by 12, 2 by 21, 4 by 17, or some value. But here what happened? Efficiency I can control. How, sir? How you can control? By controlling temperature, T1, T2. When the gas expands, isothermal expansion, I'll control the temperature of the gas. At what temperature I'll make it to expand? At that temperature, what happened? That will be T1. At what temperature the isothermal compression occurs? That is T2. By varying T1, T2, what I can control efficiency. I think this is something very, very essential. That's what the Carnot, yes, tried, because he was interested to control that efficiency. Why to control, sir? Why to control efficiency? Because I want to improve it. You see, all the previous problems, the efficiency what will happen was a fixed value. And it was dependent upon the type of gas. Am I right? If monatomic gas, you'll get one value. If it's a diatomic gas, you'll get one value. Did you notice? Because I would have said this, but I wanted to students to notice. So if you have a notes, everything, okay, what all we done previous topic, you just go there and check it. No, monatomic gas we have discussed. If you make it diatomic, the efficiency will change. So therefore, well, the efficiency depends upon the gas or what you can say working substance. The answer is yes. So what you can say answer is definitely depends on working substance. What about here? I'm going to say that it is independent of working substance. Means whether you take monatomic gas, whether you take monatomic gas or a diatomic gas, irrespective, no. So any gamma is playing role here. Please look at all of you. Is there any role of gamma? Sir, gamma is here, but any final expression, gamma will play role? No. It just depends only on T1, T2. So therefore, for the first time, you have encountered where efficiency is independent of working substance, whether it is isothermal, so whether it's a monatomic, diatomic, or mixture of gases, whatever you want, you take working substance. The efficiency depends only on these two. Okay, let's go for our heat engine. Let's go for our heat engine. Let me take this. I need this graph again. It's a very, very, you can say revolution in total mechanical engineering. So what all we have, petrol, diesel engines, no, are just based on this. And if you look at the Carnot, no, almost some more than 15 years, he has struggled to propose and construct this heat engine. So science is not that easier. What you are thinking, it will come. Okay, yeah. If I take admission in good college, some good teacher, okay, science will come. Not possible. Science will come only when you think. So there's a one best example what Carnot heat engine, what you have. He has struggled almost 15 years, sir. Sir, what is there in this? Within 10 minutes you have discussed. We have discussed 10 minutes. But to get this idea, it's not that easy. What happened? He used to draw the different, see, we have discussed so many numericals, no? That was all tried by Carnot. He wanted the efficiency independent of the working substance, independent of gas. Nature of gas should not play a role. That's what when he used to draw so many cycles and used to check. Finally, what when he got an idea, okay, if I do like this, then luckily what when he was able to end up an expression for efficiency which is independent of nature of gas. So what is our engine? I think we had our engine like this, no? This is the, it's a very important as a student. I feel like they are the inspiration for you. Such things, no, such concepts, no, they are inspiration. They'll help you a lot. Oh, so they'll help you to lot to understand the science.